A university study compared a 2,000-year-old desert house to a building with full air conditioning and measured which one stayed cooler. The ancient one won. No electricity, no mechanical cooling, just earth walls thick enough to delay the sun's heat by 12 hours. These homes still stand in Yemen, and they have worked for 2,000 years. Yet, after 1950, earthen construction collapsed by 70%. The reason we abandoned them has nothing to do with whether they work. In the heart of Yemen's Hadramaut Valley, the city of Shibam took shape nearly 2,000 years ago, pressed between the harsh desert and the narrow lifeline of the Wadi. Here, every square meter of fertile land mattered. Crops, animals, and people competed for the same thin ribbon of green, hemmed in by endless sand and the threat of sudden flood. The solution was not to spread out, but to build upward. By the 1st century CE, families began stacking mud brick homes into vertical towers, some rising 5, 6, even 10 stories high. These towers clustered together, forming a dense skyline that seems to defy the desert's emptiness. The need for security was just as urgent as the need for space. Tribal raids and shifting alliances made isolation dangerous. High, windowless ground floors acted as fortresses, while upper levels sheltered generations of extended family. The result was a city that grew taller instead of wider, conserving every patch of arable ground while creating a living wall against both human and natural threats. Archaeological surveys and medieval travelers' accounts describe a labyrinth of narrow streets, shaded alleys, and compact plots that forced buildings to share walls and minimize exposed surfaces. This urban logic was born out of necessity. Shibam's towers were not an architectural flourish, but a direct answer to the land's scarcity and the ever-present risks of desert life. The city itself became a kind of organism, adapting to survive in a place where every resource was precious and every design choice carried weight. These pressures would shape not just the skyline, but the way people lived, worked, and stayed cool in an environment that offered little margin for error. Inside Shibam's towers, daily life unfolded in vertical layers, each floor shaped by both necessity and tradition. The ground level, thick-walled and windowless, sheltered livestock and stored grain, its cool darkness a buffer against the midday heat. Above, the middle floors served as the heart of family life. Here, women prepared meals in shaded kitchens, children played in open halls, and elders gathered for afternoon tea, shielded from the sun by deep-set windows and heavy wooden shutters. At the very top, breezy rooms with open latticework caught the faintest winds, reserved for honored guests or for sleeping during the hottest nights. Central courtyards anchored this vertical rhythm. Each morning, sunlight filtered down to the courtyard floor, where families performed ablutions, shared breakfast, and tended to small gardens or water jars. The courtyard was more than a private retreat. It acted as a communal lung, drawing in cool air and venting warm air upward through the tower's core. Seasonal rituals revolved around this space, from the breaking of fasts to the celebration of festivals. Maintaining these earthen homes required collective effort. Every year, after the brief rains, skilled plasterers, often organized in traveling guilds, arrived to renew the protective lime salt coating on the tower's facades. This was no small task. Neighbors pooled resources, mixing new plaster from local silt, straw, and palm fiber, then spreading it by hand over every exposed surface. The work was as much social as technical, blending craft, ritual, and community pride. These annual gatherings ensured that the buildings endured both climate and time, reinforcing bonds between families and preserving the city's distinctive skyline. The care invested in each wall and courtyard laid the foundation for the remarkable comfort and resilience that would later draw the attention of architects and scientists alike. Walls nearly half a meter thick form the backbone of Shibam's towers. Made from sun-dried mud brick, these dense barriers act as enormous thermal batteries, absorbing heat during the day and holding it back from the living spaces inside. When the desert sun climbs past 40 degrees Celsius, the outer surface of the wall soaks up energy, but the heat moves so slowly through the mass that it does not reach the interior until long after sunset. This delay, known as thermal lag, stretches for 8 to 12 hours in a typical 45 centimeter wall. By the time the warmth finally seeps through, night air has cooled and the cycle reverses. Stored heat is released just as the outside world is losing its edge, flattening the daily temperature swing inside by several degrees. Shibam's builders did not stop at thick walls. They knew that direct sunlight was the enemy of comfort. Overhanging eaves, deep-set windows, and wooden lattice screens, mashrabiyah, cut down the amount of solar energy striking the facade by up to 75%. Even the city's narrow alleys and shared party walls play a role, keeping most surfaces shaded for much of the day. The result is a dramatic reduction in solar gain, measured in modern studies as a drop from 850 watts per square meter on bare walls to just 200 watts per square meter when protected by screens and eaves. High albedo lime plaster, renewed annually, reflects even more energy away, letting the Earth's mass do its work without being overwhelmed. These two strategies, thermal mass and aggressive shading, form the passive system's first line of defense, setting the stage for airflow and courtyard cooling to do the rest. AER in a desert courtyard is never still for long. As the morning sun strikes the courtyard floor, the air inside begins to warm and rise, pulling cooler air from shaded alleys and lower rooms. This simple movement sets the entire house in motion, acting like a natural pump that refreshes the interior without a single fan or compressor. The effect is strongest in towers with a central courtyard open to the sky. Here, the stack effect and cross ventilation work together. Hot air escapes upward, while breezes, channeled by narrow lanes and thick walls, drive a gentle current from one shaded space to the next. Water adds another layer of cooling. Shallow basins or damp sand placed at the center of the courtyard cool the air through evaporation. As dry desert air passes over the wet surface, it picks up moisture and loses heat. Field measurements in Persian and Arabian courtyard houses show that this evaporative effect can lower courtyard air temperatures by up to 4 degrees Celsius on the hottest days. In some cases, a small reflecting pool or a series of water jars is enough to tip the balance from stifling to comfortable, especially in the late afternoon when the sun is at its peak. Researchers have put these claims to the test. In a side-by-side study, a traditional earthen courtyard house and a modern concrete apartment were monitored during a full summer. The results are striking. The courtyard house kept its main rooms below 35 degrees Celsius for over 70% of daytime hours, with no mechanical cooling at all. Meanwhile, the concrete apartment needed constant air conditioning to achieve the same comfort, consuming more than 150 kilowatt hours of electricity per day. The passive house not only matched, but in some cases outperformed, the modern building, using nothing but airflow, water, and the physics of heat. These findings are now prompting a new look at ancient methods, raising a pressing question. If these strategies work so well, why did we ever stop building this way? In the decades after World War II, the world's desert saw a dramatic change in how homes were built. Cement factories scaled up, and reinforced concrete arrived by rail and truck, promising speed, strength, and a new image of progress. In Yemen, the opening of the Aden port to international shipping in the early 20th century made Portland cement and fired brick widely available for the first time. By the 1950s and the 1960s, earthen brick production in many regions collapsed, dropping by as much as 70% within a single generation. Colonial authorities and local officials began to view mud brick as old-fashioned, even unsanitary. In some territories, like the Spanish-controlled Canary Islands, a decree in 1892 required new buildings to use stone or fired brick, citing fire safety and hygiene. Even where such rules were not written for Shibam itself, the pressure to modernize was unmistakable. The cement industry's expansion, combined with new building materials and shifting policy, set in motion a steady retreat from the craft of earthen construction, long before labor costs or building codes finished the job. By the late 20th century, the economics of building with earth had changed beyond recognition. Skilled masons who once shaped and stacked mud brick by hand saw their wages triple between 1975 and 1995. A jump driven by labor shortages, migration, and the rising costs of artisanal work. What had been a communal craft became a specialized trade, priced out of reach for most families. Meanwhile, building codes in Yemen and across the region began to mirror international standards. New rules restricted the height of unreinforced earthen walls, mandated steel reinforcement for anything above 2 stories, and required expensive engineering reviews for traditional designs. The language of these codes favored concrete and fired brick, effectively sidelining centuries-old techniques. Contractors, faced with higher labor bills and regulatory red tape, turned to prefabricated panels and poured concrete, materials that met the letter of the law and could be installed by less expensive, less skilled workers. The result was a construction industry locked into a cycle. Cheap energy powered mechanical cooling, while the knowledge and economics that once supported passive, climate-responsive architecture faded from daily practice. As global temperatures rise and cities strain under record heat, the logic of climate-responsive design grows urgent. Modern comfort still leans on finite energy, yet the lessons of ancient architecture remain. Sometimes progress means rediscovering what we once knew. What would our cities feel like if we listened